Hello, Namaste. Myself Ankita Shreya Prasad, and you are listening to along with our NCERT 11th and 12th audio video book presented by ART.SKILL.PASSION. Chapter 3 Current Electricity 3.1 Introduction. In Chapter 1, all charges, whether free or bound, were considered to be at rest. Charges in motion constitute an electric current. Such currents occurs naturally in many situations. Lightning is one such phenomenon in which charges flow from the clouds to the earth through the atmosphere, sometimes with disastrous results. The flow of charges in lightning is not steady, but in our everyday life we see many devices where charges flow in steady manner, like water flowing smoothly in a river, a torch and a cell-driven clock are examples of such devices. In the present chapter, we shall study some of the basic laws concerning steady electric currents. 3.2 Electric current. Imagine a small area held normal to the direction of flow of charges. Both the positive and the negative charges may flow forward and backward across the area. In a given time interval t, let q plus be the net amount, that is, forward minus backward, of positive charge that flows in forward direction across the area. Similarly, let q minus be the net amount of negative charge flowing across the area in the forward direction. The net amount of charge flowing across the area in forward direction in the time interval t then is q is equal to q plus minus q minus. This is proportional to t for steady current, and the quotient I is equal to q divided by t is defined by the current across the area in the forward direction. If it turns out to be negative number, it implies a current in the backward direction. Currents are not always steady, and hence more generally we define the current as follows. Let delta Q be the net charge flowing across the cross section of a conductor during the time interval delta T, that is between the times T and T plus delta T. Then the current at time T across the cross section of the conductor is defined as the value of the ratio of delta Q to delta T in the limit of delta T tending to 0. I into T is equal to limit delta T tends to 0 delta Q divided by delta T. In SI units, the unit of current is ampere. An ampere is defined through magnetic effects of currents that we'll study in the following chapter. An ampere is typically the order of magnitude of currents in domestic applications. An average lightning carries currents of the order of tens of thousands of amperes, and at the outer extreme, currents in our nerves are in microamperes. 3.3 Electric current in conductor. An electric charge will experience a force if an electric field is applied. If it is free to move, it will thus move, contributing to a current. In nature, free charge particles do exist, like an upper strata of atmosphere called the ionosphere. However, in atoms and molecules, the negatively charged electrons and the positively charged nuclei are bound to each other and are thus not free to move. Bulk matter is made up of many molecules. A gram of water, for example, contains approximately 10 to the power 22 molecules. These molecules are so closely packed that the electrons are no longer attached to individual nuclei. In some materials, the electrons will still be bound, that is, they will not accelerate even if an electric field is applied in other materials. Notably, metals, some of the electrons are partially free to move within the bulk material. These materials, generally called conductors, develop electric currents in them when an electric field is applied. If we consider solid conductors, then of course the atoms are tightly bound to each other, so that the current is carried by the negatively charged electrons. There are, however, other types of conductors like electrolytic solutions where positive and negative charges both can move. In our discussions, we will focus only on solid conductors so that the current is carried by the negatively charged electrons in the background of fixed positive ions. Consider first the case when no electric field is present. The electrons will be moving due to thermal motion during which they collide with the fixed ions. An electron colliding with an ion emerges with the same speed as before the collision. However, the direction of its velocity after the collision is completely random. At a given time, there is no preferential direction for the velocities of the electrons. Thus, on the average, the number of electrons traveling in any direction will be equal to the number of electrons traveling in the opposite direction. So, there will be no net electric current. Let us now see what happens to such a piece of conductor if an electric field is applied in the shape of cylinder of radius R. Figure 1.3. Figure 1.3, charge plus Q and minus Q put at the ends of a metallic cylinder. The electrons will drift because of the electric field created to neutralize the charges. The current thus will stop after a while unless the charges plus Q and minus Q are continuously replenished. Suppose we now take two thin circular discs of dielectric of the same radius and put positive charge plus Q distributed over one disc and similarly minus Q at the other disc. We attach the two discs on the two flat surfaces of the cylinder. An electric field will be created and is directed from the positive towards the negative charge. The electrons will be accelerated due to this field towards plus Q. They will thus move to neutralize the charges. The electrons, as long as they are moving, will constitute an electric current. Hence, in the situation, consider there will be a current for a very short while and no current thereafter. We can also imagine a mechanism where the ends of the cylinder are supplied with the fresh charges to make up of any charges neutralized by electrons moving inside the conductor. In that case, there will be a steady electric field in the body of the conductor. This will result in continuous current rather than a current for a short period of time. Mechanisms which maintain a steady electric field are cells or batteries that we shall study later in this chapter. In the next sections, we shall study the steady current that results from a steady electric field in conductors. 3.4 Ohm's law. A basic law regarding flow of currents was discovered by G.S. Ohm in 1828, long before the physical mechanism responsible for flow of currents was discovered. Imagine a conductor through which a current I is flowing and let V be the potential difference between the ends of the conductor. Then Ohm's law states that V is directly proportional to I or V is equal to Ri. With the constant proportionality, R is called the resistance of the conductor. The SI units of resistance is ohm and is denoted by the symbol ohm. The resistance R not only depends on the material of the conductor but also the dimensions of the conductor. The dependence of R on dimensions of the conductor can easily be determined as follows. Consider a conductor satisfying equation 3.3 to be in the form of a slab of length L and cross-sectional area A. Figure 3.2a. Imagine placing two such identical slab slides by slide. Figure 3.2b. So that the length of the combination is 2L. The current flowing through the combination is the same as the flowing through either of the slabs. If V is the potential differences across the ends of the first slab, then V is also the potential difference across the ends of the second slab. Since the second slab is identical to the first and the same current I flows through both, the potential difference across the ends of the combination is clearly sum of the potential difference across the two individual slabs and hence equals 2V. The current through the combination is I and the resistance of the combination RC is from equation 3.3. RC is equal to 2V divided by I is equal to 2R. Since V divided by I is equal to R, the resistance of either of the slabs, thus doubling the length of conductor doubles the resistance. In general, then the resistance is proportional to length. R is directly proportional to L. Next, imagine diving the slabs into 2 by cutting it lengthwise, so that the slab can be considered as a combination of two identical slabs of length L, but each having a cross-sectional area of A divided by 2. Figure 3.2c. For a given voltage V across the slab, if I is the current through the entire slab, then clearly the current flowing through each of the two half slabs is I divided by 2. Since the potential difference across the ends of the half slabs is V, that is the same as across the first slab, the resistance of each of the half slabs R1 is equal to V divided by I divided by 2 is equal to 2 V divided by I is equal to 2R. Thus, having the area of cross section of conductor doubles the resistance. In general, the resistance R is inversely proportional to the cross sectional area. R is directly proportional to 1 divided by A. Combining equation 3.5 and 3.7, we have R is directly proportional to L divided by A. And hence for a given conductor, R is equal to rho L by A. With the constant of proportionality, rho depends on the material of the conductor but not on its dimensions. Rho is called resistivity. Using the last equation, Ohm's law reads V is equal to IR is equal to I rho L by A. Current per unit area taken normal to the current I divided by A is called current density and is denoted by J. The SI units of the current density are A meter square. Further, if E is the magnitude of the uniform electric field in the conductor whose length is L, then the potential difference V across its ends is EL. Using these, the last equation reads EL is equal to J rho L. E is equal to J rho. The above relations for the magnitudes E and J can indeed be cast in the vector form. The current density, which we have defined as the current through unit area normal to the current, is also directed along E and is also a vector J. JE divided by E. Thus the last equation can be written as E is equal to J rho. J is equal to rho E, where sigma is equal to 1 divided by rho is called the conductivity. Ohm's law is often stand in an equivalent form. In addition to equation 3.3, in the next session, we will try to understand the origin of the Ohm's law as arising from the characteristics of the drift electrons. 3.5 Drift of electrons and the origin of resistivity. As remarked before, an electron will suffer collision with the heavy fixed ions, but after collision, it will emerge with the same speed but in random direction. If we consider all the electrons, their average velocity will be 0 since their directions are random. Thus, if there are n electrons and the velocity of ith electrons I is equal to 1 to 3 and so on, n at given time is Vi, then 1 divided by n sigma Vi is equal to 0. Consider now the situation when an electric field is present, electrons will be accelerated due to this field by A is equal to minus small e and capital E divided by m, where minus E is the charge and m is the mass of an electron. Consider again the ith electron at a given time t. This electron would had its lost collision sometime before t, and let ti be the time elapsed after its last collision. If vi was its velocity immediately after the last collision, then its velocity vi at time t is vi is equal to vt plus minus e capital E divided by m ti. Since starting with its last collision, it was accelerated. Figure 3.3 with an acceleration given by equation 3.15 for a time interval ti, the average velocity of the electrons at time t is the average of all the vi's. The average of vi's is 0. Since immediately after any collision, the direction of the velocity of an electron is completely random. The collisions of the electrons do not occur at regular intervals but at random times. Let us denote by the Tesla. The average time between the successive collision, then at a given time, some of the electrons would have spent time more than Tesla and some less than Tesla. In other words, the time ti in the equation 3.16 will be less than Tesla for some and more than for others as we go through the values I is equal to 1, 2 and so on, and the average value of ti then tau known as relaxation time. Thus averaging equation 3.16 over the n electrons at any given time t gives us for the average velocity Vd. Vd is equal to Vi average is equal to Vi average minus small e into capital E divided by m ti average is equal to 0 minus small e into capital E divided by m. Tau is equal to minus small e into capital E divided by m tau. This lost result is surprising. It tells us that the electrons move with an average velocity which is independent of the time, although electrons are accelerated. This is the phenomenon of drift, and the velocity Vd in equation 3.17 is called the drift velocity. Because of the drift, there will be net transport of charges across any area perpendicular to E. Consider a planar area A located inside the conductor such that the normal to the area is parallel to E. Then, because of the drift in an infinitesimal amount of time delta t, all electrons to the left of the area distance up to mode Vd sigma t would have crossed the area. If n is the number of free electrons per unit volume in the metal, then there are n delta t mode Vd a such electrons, since each electron carries a charge minus e. The total charge transported across this area a to the right in time delta t is minus ne a Vd into delta t is directed towards the left, and hence the total charge transported along the E across the area is negative of this. The amount of charge crossing the area A in time delta t is by definition equation 3.2 I delta t, where I is the magnitude of the current. Hence I delta t is equal to Ne A Vd delta t. Substituting the value of mode Vd from equation 3.17, I delta t is equal to E square A divided by m tau n delta t mode E. By definition, I is related to the magnitude of mode J of current density by I is equal to mode Ja. Hence for equation 3.19 and 3.20, J is equal to Ne square divided by m tau mode E. The vector J is parallel to E, and hence we can write in the vector form J is equal to Ne square divided by m tau E. Comparison with equation 3.13 shows that equation 3.22 is exactly the Ohm's law. If we definitely the conductivity sigma as sigma is equal to Ne squared divided by M2. We thus see that a very simple picture of electrical conduction reproduce Ohm's law. We have of course made assumption that τ and N are constants independent of E. We shall in the next section discuss the limitations of Ohm's law. 3.5.1 Mobility. As we have seen, conductivity arises from mobile charge carriers in metals. These mobile charges carriers are electrons in an ionized gas. They are electrons and positive charged ions. In an electrolyte, these can be both positive and negative ions. An important quantity is the mobility, nu, defined as the magnitude of the drift velocity per unit electric field. Nu is equal to mod Vd divided by E. The SI unit of mobility is meter square Vs and is 10 to the power 4 of mobility in the practical unit centimeter square Vs. Mobility is positive from equation 3.17. We have Vd is equal to E tau E divided by M. Hence nu is equal to Vd divided by E is equal to V tau divided by M, where tau is the average collision time for electrons. 3.6 Limitations of Ohm's law. Although Ohm's law has been found valid over a large class of materials, there do exist materials and devices used in electric circuits where the proportionality of V and I does not hold. The deviation broadly are one or more of the following types. A. V ceases to be proportional to I. B. The relation between V and I depends on the sign of V. In other words, if I is the current for a certain V, then revising the direction of V keeping its magnitude fixed does not produce a current of the same magnitude as I in the opposite direction. Figure 3.6. This happens for example in a diode which we will study in chapter 14. C. The relation between V and I is not unique, that is, there is more than one value of V for the same current I. A material exhibiting such behavior is GaAs. Materials and devices not obeying Ohm's law in the form of equation 3.3 are actually widely used in electronic circuits. In this and a few subsequent chapters, however, we will study the electrical currents in materials that obey Ohm's law. 3.7 Resistivity of various materials. The resistivity of various common materials are listed in table 3.1. The materials are classified as conductors, semiconductors and insulators depending on their resistivities. In an increasing order of their values, metals have low resistivities in the range of 10 to the power minus 8 ohm m to 10 to the power minus 6 ohm m. At the other end are insulators like ceramic, rubber and plastic having resistivities of 10 to the power 18 times greater than metals or more. In between the two are the semiconductors. These however have resistivities characteristically decreasing with a rise in temperature. The resistivities of semiconductors can be decreased by adding small amount of suitable impurities. This last feature is exploited in use of semiconductors for electronic devices. Table 3.1 Chemically produced resistors for domestic use or in laboratories are of two major types: wire-bound resistors and carbon resistors. Wire-bound resistors are made by winding the wires of an alloy, that is magnesium, constantan, nichrome or similar ones. The choice of these materials is dedicated mostly by the fact that their resistivities are relatively insensitive to temperature. These resistors are typically in the range of a fraction of an ohm to a few hundred ohms. Resistors in the high range are made mostly from carbon.
Carbon resistors are compact, inexpensive, and thus find extensive use in electron circuit. Carbon resistors are small in size and hence their values are given using a color code. Table 3.2 Resistor color codes: black 0, brown 1, red 2, orange 3, yellow 4, green 5, blue 6, violet 7, grey 8, white 9. And gold 5% tolerance, silver 10% tolerance, no color 20% tolerance. The resistors have a set of coaxial colored rings on them whose significance are listed in table 3.2. The first two bands from the end indicate the first two significant figures of the resistance in ohms. The third band indicates the decimal multiplier as listed in table 3.2. The last band stands for tolerance or possible variation in percentage about the indicated values. Sometimes this last band is absent and that indicates a tolerance of 20%. For example, if the four colors are orange, blue, yellow and gold, the resistance value is 36 into 10 to the power 4 ohm with a tolerance value of 5%. 3.8 Temperature dependence of resistivity. The resistivity of a material is found to be dependent on the temperature. Different materials do not exhibit the same dependence on temperature over a limited range of temperatures that is not too large. The resistivity of a metallic conductor is approximately given by rho T is equal to rho naught 1 plus alpha T minus T naught, where rho T is the resistivity at a temperature T and rho naught is the same at a reference temperature T naught, and alpha is called temperature coefficient of resistivity, and from equation 3.26 the dimension of sigma is temperature minus 1. For metals, alpha is positive and values of alpha for some metals at T naught is equal to 0 degrees Celsius are listed in table 3.1. The relation of equation 3.26 implies that a graph of rho naught plotted against T would be a straight line. At temperature much lower than 0 degrees Celsius, the graph, however, deviates considerably from a straight line. Equation 3.26 thus can be used approximately over a limited range of T around any reference temperature T naught, with the graph can be approximated as a straight line. Some materials like nichrome, which is an alloy of nickel, iron and chromium, exhibit a very weak dependence of resistivity with temperature. Figure 3.10. Magnin and constantan have similar properties. These materials are thus widely used in wire-bound standard resistors since their resistance values would change very little with temperatures. Unlike metals, the resistivities of semiconductors decrease with the increasing temperature. A typical dependence is shown in figure 3.11. We can quantitatively understand the temperature dependence of the resistivity in the light of our deviation of equation 3.23 from the equation. Resistivity of a material is given by rho is equal to 1 divided by sigma is equal to m divided by n e square tau. Rho thus depends inversely both on the number n of free electrons per unit volume and on the average time tau between collisions. As we increase temperature, average speed of the electrons which act as the carrier of current increases, resulting in the more frequent collisions. The average time of collisions tau thus decreases with temperature. In a metals, n is not dependent on temperature to any applicable extent, and thus the decrease in the value of tau with rise in temperature cause rho to increase as we have observed. For insulators and semiconductors, however, n increases with temperature. This increase more than compensates any decrease in equation 3.23, so that for such materials rho decreases with temperature. 3.9 Electrical energy power. Consider a conductor with endpoint A and B in which a current I is flowing from A to B. The electric potential at A and B are denoted by VA and VB respectively. Since current is flowing from A to B, VA greater than VB, and potential difference across AB is V is equal to VA minus VB greater than 0. In a time interval delta t, an amount of charge delta q is equal to 1 delta t travels from A to B. The potential energy of the charges at A by definition was QV and A, and similarly at B it is QVB. Thus charge in the potential energy delta U pot is equal to final potential energy minus initial potential energy is equal to delta QVB minus VA is equal to minus delta QV is equal to minus IV delta T lesser than 0. If charges moved without collision through the conductor, their kinetic energy would also change so that the total energy is uncharged. Conservation of total energy would then imply that delta K is equal to minus delta U pot, that is delta K is equal to IV delta T greater than 0. Thus, in case charges were moving freely through the conductor using the action of electric field, their kinetic energy would increase as they move. We have, however, seen earlier that on the average, charge carriers do not move with acceleration but with a steady drift velocity. This is because of the collision with ions and atoms during transit. During collision, the energy gained by the charges thus is shared with the atoms. The atoms vibrate more vigorously, that is, the conductor heats up. Thus, in an actual conductor, an amount of energy dissipated as heat in the conductor during the time interval delta T is delta W is equal to IV delta D. The energy dissipated per unit time is the power dissipated. P is equal to delta W divided by delta T, and we have P is equal to IV. Using Ohm's law, V is equal to IR, we get P is equal to I square R is equal to V square R.
As the power loss, ohmic loss in a conductor of resistance are carrying a current I. It is this power which eats up, for example, the coil of an electric bulb to incandescence, radiating out heat and light. Where does the power come from? As we have reasoned before, we need an external source to keep a steady current through the conductor. It is clearly this source which must supply this power. In the simple circuit shown with a cell, it is the chemical energy of the cell which supplies this power for as long as it can. The expression for power, equation 3.32 and 3.33, show the dependence of the power dissipated in a resistor R on the current through it and the voltage across it. Equation 3.33 as an important application to power transmission. Electrical power is transmitted from power station to homes and factories, which may be hundreds of miles away, via transmission cables. One obviously wants to minimize the power loss in the transmission cables connecting the power station to homes and factories. We shall see now how this can be achieved. Consider a device R to which a power P is to be delivered via transmission cables have a resistance RC to be dissipated by it. Finally, if V is the voltage across R and I the current through it, then P is equal to VI. The connecting wires from the power station to the device has a finite resistance RC. The power dissipated in the connecting wires which is wasted is PC, with PC is equal to I square RC is equal to P square RC divided by V square. From
Equation 3.32 thus to drive a device of power P, the power wasted in the connecting wires is inversely proportional to V square. The transmission cables from power stations are hundreds of miles long and their resistance RC is considerable. To reduce PC, these wires carry current at enormous values of V, and this is the reason for the high voltage danger signs on transmission lines. A common sight as we move away from populated areas using electricity at such voltages is not safe, and hence at the other end a device called transformer lowers the voltage to a value suitable for use. 3.10 Combination of resistors, series and parallel. The current through a single resistor R across which there is a potential difference V is given by Ohm's law. I is equal to VR. Resistors are sometimes joined together and there are simple rules for calculation of equivalent resistance of such combination. Figure 3.13. A series combination of two resistors R1 and R2. Two resistors are said to be in series if only one of their endpoints is joined. Figure 3.13. If a third resistor is joined with the series combination of the two, figure 3.14, then all three are said to be in series. Clearly, we can extend this definition to series combination of any number of resistors. Figure 3.14. A series combination of three resistors R1, R2, R3. Two or more resistors are said to be in parallel if one end of all the resistor is joined together and similarly the other ends joined together. Figure 3.15. Figure 3.15. Two resistors R1, R2 connected in parallel. Consider two resistors R1 and R2 in series. The charge which leaves R1 must be entering R2 since current measures the rate of flow of charge. This means the same current I flows through R1 and R2. By Ohm's law, potential difference across R1 is equal to V1 is equal to IR1 and potential difference across R2 is equal to V2 is equal to IR2. The potential difference V across the combination is V1 plus V2, hence V is equal to V1 plus V2 is equal to IR1 plus R2. This is as if the combination had an equivalent resistance Req, which by Ohm's law is Req is equal to V divided by I is equal to R1 plus R2. If we had three resistors connected in series, then similarly V is equal to IR1 plus IR2 plus IR3 is equal to IR1 plus R2 plus R3. This obviously can be extended to a series combination of any numbers n of the resistors R1, R2 and so on are, and the equivalent resistance Req is equal to R1 plus R2 plus so on Rn. Consider now the parallel combination of two resistors. Figure 3.15. Charge that flows in at A from the left flows out partly through R1 and partly through R2. The currents I1, I2 shown in the figure are the rates of flow of charge at the point indicated. Hence, I is equal to I1 plus I2. The potential difference between A and B is given by Ohm's law applied to R1. V is equal to I1 R1. Also, Ohm's law applied to R2 gives V is equal to I2 R2. Therefore, I is equal to I1 plus I2 is equal to V by R1 plus V by R2 is equal to V 1 by R1 plus 1 by R2. If the combination was replaced by an equivalent resistance Req, we would have by Ohm's law I is equal to V divided by Req, hence 1 by Req is equal to 1 by R1 plus 1 by R2. We can easily see how this extends to three resistors in parallel. Figure 3.16. Figure 3.16. Parallel combination of three resistors R1, R2 and R3. Exactly as before, I is equal to I1 plus I2 plus I3, and applying Ohm's law to R1, R2 and R3, we get V is equal to I1 R1, V is equal to I2 R2, V is equal to I3 R3. So that I is equal to I1 plus I2 plus I3 is equal to V into 1 by R1 plus 1 by R2 plus 1 by R3.
An equivalent resistance Req that replaces the combination would be such that I is equal to V by Req, and hence 1 by Req is equal to 1 by R1 plus 1 by R2 plus 1 by R3. We can reason similarly for any number of resistors in parallel. The equivalent resistance of n resistors R1, R2, so on Rn is R1 by Req is equal to 1 by R1 plus 1 by R2, so on 1 by Rn. This formula of equivalent resistance can be used to find out currents and voltage in more complicated circuit. Consider for example the current in figure 3.17, where there are 3 resistors R1, R2 and R3. R2 and R3 are in parallel, and hence we can replace them by an equivalent Req23 between point B and C, with 1 divided by Req23 is equal to 1 by R2 plus 1 by R3, or Req23 is equal to R2 R3 by R2 plus R3. The circuit now has R1 and Req23 in series, and their combination can be replaced by an equivalent resistance with Req123 is equal to Req23 plus R1. If the voltage between A and C is V, the current I is given by I is equal to V divided by Req123 is equal to V divided by R1 plus R2 R3 divided by R2 plus R3 is equal to V into R2 plus R3 divided by R1 R2 plus R1 R3 plus R2 R3. 3.11 Cells EMF internal resistance. We have already mentioned that a simple device to maintain a steady current in an electric circuit is the electrolytic cell. Basically, a cell has 2 electrodes called the positive P and negative, and as shown in the figure 3.18, they are immersed in an electrolytic solution dipped in the solution. The electrodes exchange charges with the electrolyte. The positive electrode has a potential difference V plus greater than 0 between itself and electrolyte solution immediately adjacent to it, marked in A in the figure. Similarly, the negative electrode develops a negative potential minus V minus greater than 0. Relate to the electrolyte adjacent to it, marked as B in the figure. When there is no current, the electrolyte has the same potential throughout, so that the potential difference between P and N is V plus. Minus of minus V is equal to V plus V minus. This difference is called the electromotive force EMF of the cell and is denoted by epsilon. That epsilon is equal to V plus V minus greater than 0. Note that epsilon is actually a potential difference and not a force. The name EMF, however, is used because of historical reason and was given at a time when the phenomenon was not understood properly. To understand the significance of epsilon, consider a resistor are connected across the cell. Figure 3.18. A current I flows across R from C to D. As explained before, a steady current is maintained because current flows from N to P through the electrolyte. Clearly, across the electrolyte, the same current flows through the electrolyte from N to P, whereas through R, it flows from P to N. The electrolyte through which a current flows has a finite resistance R, called the internal resistance. Consider first the situation when R is infinite, so that I is equal to V divided by R is equal to 0, where V is the potential difference between P and N. Now V is equal to potential difference between P and A plus potential difference between A and B plus potential difference between B and N is equal to epsilon. Thus, EMF epsilon is the potential difference between the positive and negative electrodes in an open circuit, that is, when no current is flowing through the cell. If, however, R is finite, I is not 0. In that case, the potential difference between P and N is V is equal to V plus V minus IR is equal to epsilon minus IR. Note the negative sign in the expression IR for the potential difference between A and B. This is because the current I flows from B to A in the electrolyte. In practical calculation, internal resistance of cell in the circuit may be neglected
when the current I is such that epsilon so greater than IR. The actual value of the internal resistance of cells vary from cell to cell. The internal resistance of dry cell, however, is much higher than the common electrolytic cells. We also observe that since V is the potential difference across R, we have from Ohm's law V is equal to IR, combining equation 3.57 and 3.58. We get IR is equal to epsilon minus IR, or I is equal to epsilon divided by R plus R. The maximum current that can be drawn from a cell is for R is equal to 0, and it is I max is equal to epsilon by R. However, in most cells the maximum allowed current is much lower than this to prevent permanent damage to the cell. 3.12 Cells in series and in parallel. Like resistors, cells can be combined together in an electric circuit, and like resistors, one can, for calculating currents and voltage in a circuit, replace a combination of cells by an equivalent cells. Figure 3.20. Two cells of EMF epsilon 1 and epsilon 2 in the series R1 R2 are their internal resistance for connections across A and C. The combination can be considered as one cell of the EMF epsilon EQ and an internal resistance REQ. Consider first two cells in series where one terminal of the two cells is joined together, leaving the other terminal in either cell free. Epsilon 1 and epsilon 2 are the EMF of the two cells and R1, R2, their internal resistance respectively. Let VA, VB, VC be the potential at a point A, B and C shown in figure 3.20. Then VA minus VB is the potential difference between the positive and negative terminals of the first cell. We have already calculated it in the equation 3.57, and hence VAB is equal to VA minus VB is equal to epsilon 1 minus IR. Similarly, VBC is equal to VB minus VC is equal to epsilon 2 minus IR. Hence, the potential difference between the terminals A and C of the combination is VAC is equal to VA minus VC is equal to VA minus VB plus VB minus VC is equal to epsilon 1 plus epsilon 2 minus IR1 plus R2. If we wish to replace the combination by a single cell between A and C of EMF epsilon equation and internal resistance REQ, we would have VAC is equal to epsilon EQ minus IREQ. Comparing the last two equations, we get epsilon EQ is equal to E1 plus E2 and REQ is equal to R1 plus R2. In figure 3.20, we had connected the negative electrode of the first to the positive electrode of the second. If instead we connect the two negatives, equation 3.61 would change to VBC is equal to minus epsilon 2 minus IR, and we will get epsilon EQ is equal to epsilon 1 minus epsilon 2, epsilon 1 greater than epsilon 2. The rule for series combination clearly can be extended to any number of cells. First, the equivalent EMF of series combination of n cells is just the sum of their individual EMFs, and second, the equivalent internal resistance of a series combination of n cell is just the sum of their internal resistance. This is so when the current leaves each cell from positive electrode, if in the combination the current leaves any cells from the negative electrode. The EMF of the cell enters the expression for epsilon EQ with a negative sign as in equation 3.66. Next, consider a parallel combination of the cells. Figure 3.21. I1 and I2 are the currents leaving the positive electrodes of the cells. At the point B1, I1 and I2 flowing in, whereas the current I flows out. Since as much charge flows in as out, we have I is equal to I1 plus I2. Let VB1 and VB2 be the potentials at B1 and B2 respectively. Then, considering the first cell, the potential difference across its terminals is VB1 minus VB2. Hence, from equation 3.57, V is equal to VB1 minus VB2 is equal to epsilon 1 minus I1 R1. Points B1 and B2 are connected exactly similar to the second cell. Hence, considering the second cell, we also have V is equal to VB1 minus VB2 is equal to epsilon 2 minus I2 R2. Combining the last three equations, I is equal to I1 plus I2 is equal to epsilon 1 minus V divided by R1 plus epsilon 2 minus V divided by R2 is equal to epsilon 1 by R1 plus epsilon 2 by R2 minus V 1 by R1 plus 1 by R2. Hence, V is given by V is equal to epsilon 1 R2 plus epsilon 2 R1 divided by R1 plus R2 minus I R1 R2 divided by R1 plus R2. If we want to replace the combination by a single cell between B1 and B2 of EMF epsilon EQ and the internal resistance REQ, we would have V is equal to epsilon EQ minus IR EQ. The last two equations should be the same, and hence epsilon EQ is equal to epsilon 1 R2 plus epsilon 2 R1. R1 plus R2. REQ is equal to R1 R2 divided by R1 plus R2. We can put this equation in a simpler way. 1 by REQ is equal to 1 by R1 plus 1 by R2. Epsilon EQ by REQ is equal to epsilon 1 plus R1 plus epsilon 2 by R2. In figure 3.21, we had just joined the positive terminals together, and similarly the two negative ones, so that the current I1, I2 flows out of positive terminals. If the negative terminals of the second is connected to positive terminal of the first, equation 3.75 and 3.76 would still be valid with epsilon 2 minus epsilon 2. Equation 3.75 and 3.76 can be extended easily. If there are n cells of EMF epsilon 1 and epsilon n and of internal resistance R1 and so on Rn respectively connected in parallel, the combination is equivalent to a single cell of EMF epsilon EQ and internal resistance REQ, such that 1 by REQ is equal to 1 by R1 plus so on 1 by Rn. Epsilon EQ by REQ is equal to epsilon 1 by R1 plus so on epsilon n divided by Rn. 3.13 Kirchhoff rules. Electric circuits generally consist of a number of resistors and cells interconnected, sometimes in a complicated way. The formula we have derived earlier for series and parallel combinations of resistors are not always sufficient to determine all the currents and potential differences in circuit. Two rules called Kirchhoff rules are very useful for analysis of electric circuits. Given a circuit, we start by labeling connects in each resistor by a symbol, say I, and a directed arrow to indicate that a current I flows along the resistors in the direction indicated. If ultimately I is determined to be positive, the actual current in the resistors is in the direction of the arrow. If I turns out to be negative, the current actually flows in a direction opposite to the arrow. Similarly, for each source, that is cells or some other source of electrical power, the positive and negative electrodes are labeled as well as a directed arrow with a symbol for the current flowing through the cell. This will tell us the potential difference V is equal to Vp minus Vn is equal to epsilon minus IR. Equation 3.57 between the positive terminal P and the negative terminal N. I here is the current flowing from N to P through the cells. If while labeling the current I through this cell, one goes from P to N, then of course V is equal to epsilon plus IR. Having clarified labeling, we now state the rules and the proof. A. Junction rule. At any junction, the sum of the currents entering the junction is equal to the sum of the current leaving the junction. This applies equally well if instead of a junction of several lines, we consider a point in a line. The proof of this rule follows from the fact that when currents are steady,
There is no accumulation of charges at any junction or at any point in line. Thus, the total current flowing in, which is the rate at which the charge flows into the junction, must equal the total current flowing out. Loop rule. The algebraic sum of the charges in the potential around any closed loop involving resistors and cells in the loop is 0. Figure 3.22. This rule is also obvious since electric potential is dependent on the location of the point. Thus, starting with any point, if we come back to the same point, the total change must be 0. In a closed loop, we do come back to the starting point and hence the rule. It should be noted that because of the symmetry of the network, the great power of Kirchhoff rules has not been very apparent in example 3.6 in a general network. There will be no such simplification due to symmetry and only by application of Kirchhoff rules to junction and closed loops. As many as necessary to solve the unknowns in the network, we can handle the problem. This will illustrate in example 3.7. 3.14 Wheatstone Bridge. As an application of Kirchhoff rules, consider the circuit shown in the figure 3.25, which is called the Wheatstone Bridge. The bridge has 4 resistors R1, R2, R3 and R4 across one pair of diagonally opposite points A and C. In the figure, a source is connected. This, that is AC, is called the battery arm. Between the other two vertices B and D, a galvanometer G, which is a device to detect currents, is connected. This line shown as BD in the figure is called the galvanometer arm. For simplicity, we assume that the cell has no internal resistance. In general, there will be current flowing across all the resistors as well as the current Ig through G. Of special interest is the case of balanced bridge, where the resistors are such that Ig is equal to 0. We can easily get the balance condition such that there is no current through G. In this case, the Kirchhoff junction rule applied to junction D and B, see the figure, immediately gives us the relation I1 is equal to I3 and I2 is equal to I4. Next, we apply Kirchhoff loop rule to closed loops A, D, B, A and C, B, D, C. The first loop gives minus I1 R1 plus 0 plus I2 R2 is equal to 0. Ig is equal to 0. On the second loop gives upon saying I3 is equal to I1, I4 is equal to I2. I2 is R4 plus 0 minus I1 R3 is equal to 0. From equation 3.81 we obtain I1 I divided by I2 is equal to R2 divided by R1. Whereas from equation 3.82 we obtain I1 by I2 is equal to I4 by R3. Hence we obtain the condition R2 by R1 is equal to R4 by R3. This last equation relating the 4 resistor is called the balance condition for the galvanometer to give 0 or null deflection. The Wheatstone Bridge and its balance condition provide a practical method for determination of an unknown resistance. Let us suppose we have an unknown resistance which we insert in the fourth arm. R4 is thus not known, keeping no resistance R1 and R2 in the first and the second arm of the bridge. We go on varying R3 till the galvanometer shows a null deflection. The bridge then is balanced, and from the balance condition, the value of the unknown resistance R4 is given by R4 is equal to R3, R2 by R1. A practical device using the principle is called the meter bridge. It will be discussed in the next section. 3.15 Meter bridge. The meter bridge is shown in figure 3.27. It consists of a wire of length 1 meter and of uniform cross-sectional area stretched, taut and clamped between two thick metallic strips bent at right angles. As shown, the metallic strip has two gaps across which the resistors can be connected. The end points where the wire is clamped are connected to a cell through a key. One end of galvanometer is connected to the metallic strip midway between the two gaps. The other end of the galvanometer is connected to a jockey. The jockey is essentially a metallic rod whose one end has a knife edge which can slide over the wire to make electrical connection. R is an unknown resistance whose value we want to determine. It is connected across one of the gaps. Across the other gap, we connect a standard known resistance S. The jockey is connected to some point D on the wire, a distance L centimeter from the end A. The jockey can be moved along the wire. The portion AD of the wire has a resistance RCML, where RCM is the resistance of the wire per unit centimeter. The portion DC of the wire similarly has a resistance RCM 100 - L. The four arms AB, BC, DA and CD with resistance RS, RCM, L and RCM 100 - L obviously form a Wheatstone Bridge with AC as the battery arm and BD the galvanometer arm. If the jockey is moved along the wire, then there will be one position where the galvanometer will show no current. Let the distance of the jockey from the end A at the balance point be L is equal to L1. The four resistance of the bridge at the balance point then are R, S, RCM, L1 and RCM 100 - L1. The balance condition equation 3.83a gives R divided by S is equal to RCM L1 divided by RCM 100 - L1 is equal to L1 divided by 100 - L1. Thus once we have found out L1, the unknown resistance R is known in the terms of the standard known resistance S by R is equal to S L1 divided by 100 - L1. By choosing various values of S, we would get various values of L1 and calculate R each time. An error in measurement of L1 would naturally result in an error in R. It can be shown that the percentage error in R can be minimized by adjusting the balance point near the middle of the bridge, that is, when L1 is close to 50 centimeters. This requires a suitable choice of S. 3.16 Potentiometer. This is a versatile instrument. It is basically a long piece of uniform wire, sometimes a few meters in length, across which a standard cell B is connected. In actual design, the wire is sometimes cut in several pieces placed side by side and connected at the ends by thick metal strip. Figure 3.28. In the figure, the wire runs from A to C. The small vertical portions are the thick metal strips connecting the various sections of the wire. A current I flows through the wire, which can be varied by a variable resistance rheostat R in the current. Since the wire is uniform, the potential difference between A and any point at a distance L from A is epsilon L is equal to psi L, where psi is the potential drop per unit length. Figure 3.28a shows an application of potentiometer to compare the EMF of two cells of EMF epsilon 1 and epsilon 2. The point marked 1, 2, 3 from a two-way key. Consider first a position of the key where 1 and 3 are connected. So that the galvanometer is connected to epsilon 1, the jockey is moved along the wire till a point N1. At a distance L1 from A, there is no deflection in the galvanometer. We can apply Kirchhoff loop rule to the closed loop A N1 G 31 A and get psi L1 plus 0 minus epsilon 1 is equal to 0. Similarly, if another EMF epsilon 2 is balanced against L2 A N2, psi L2 plus 0 minus epsilon 2 is equal to 0. From the last two equations, epsilon 1 by epsilon 2 is equal to N1 by L2. The simple mechanism that allows one to compare the EMFs of any two sources, epsilon 1, epsilon 2, in practice one of the cells is chosen as a standard cell whose EMF is known to a high degree of accuracy. The EMF of the other cell is then easily calculated from equation 3.92. We can also use a potentiometer to measure the internal resistance of a cell. For this, the cell EMF epsilon, whose internal resistance R is to be determined, is connected across a resistant box through a key
K2 as shown in the figure with key K2 open balance is obtained at length L1 AN1, then epsilon is equal to psi L1. When the key K2 is closed, the cells sends a current I through the resistant box R. If V is the terminal potential difference of the cell and balance is obtained at a length L2 AN2, V is equal to psi L2. So we have epsilon by V is equal to L1 by L2, but epsilon is equal to IR plus capital R and V is equal to IR. This gives epsilon by V is equal to R plus R divided by R. From equation 3.92a and 3.94b, we have R plus R divided by R is equal to L1 divided by L2. Small r is equal to capital R N2 L1 by L2 minus 1. Using equation 3.95, we can find the internal resistance of a given cell. The potentiometer has the advantage that it draws no current from the voltage source being measured. As such, it is unaffected by internal resistance of the source.
Thank you for being till the end. I hope this has helped you. If so, give thumbs up, like, share, comment, save, download and subscribe. You can support us by following in other platforms. That link is in the description. Well, thank you. See you later. Maybe never.